Okay, let's begin. So, first things first, announcements. Our first test number 1. Test 1 is on Friday next week, which I think is the 28th. So, what does that mean and what do we have to pay attention to? So, next Tuesday, no quiz. So next week, the only testing situation you're going to have to worry about is the actual test on Friday. And 2, a review will be posted. I'll post it today, a week out on the class website. I forgot the actual web link, but it's Jhevon.org/teaching. And then you click on the 1203 class. And I would say follow the instructions. Alright, so I'll post a review. It will be essentially in the form of a mock test where I'll say, okay, this is what your test is going to look like. But I'll, of course, give you instructions about how to go about studying before the test and what to do to follow up after you've actually done the test. But the idea is, for best results, you really want to take it as a mock test. So you want to study before, and then when you actually take the mock test, pretend it's a real test, right? So you probably don't want to jump straight into it. Even if I post it today, probably you shouldn't look at it today. Probably what you should do instead is study the topics that I'm going to mention, do extra practice problems, and then when you do the test, maybe by next Tuesday or so, pretend it's a test, sit down, time yourself, do the test, right? Then you can follow up on that, and you can see me in office hours on Wednesday to kind of go over anything that you thought you might have missed, or just follow. So I'll give you instructions here about how to actually take the review, but I'll post a review. So we're not going to be doing a review in class, I'm just going to post it online. And the review is up to you, and you reach out to me if you have any issues. So it will cover everything we've done up to today. Just the 21st. So pretty much everything up to implicit differentiation. We're going to do just more implicit differentiation today, although at the end I'm going to give you a little trick that you can use alongside implicit differentiation for problems that are a little bit more complicated. But ultimately, everything we've done up to implicit differentiation is what the test is going to be. Yes?
Will there be like algebra on there as well? Like how we did the review for the first week of class?
Not directly, no.
Okay.
But of course, if you're doing something like a quotient rule, you might have to know the algebra to be able to simplify that. But so the algebra will be incidental. I'm not going to directly test you on any algebra. Probably the closest thing I would do to testing you on algebra is I might ask you to solve exponential and log equations. And so, probably not this easy, but just off the top of my head, like this, solve that equation or something like that. That's the closest thing you'll have to algebra, because I'll ask you about logs and exponentials separately since we actually covered that in class. But yeah. But other than that, you have to remember all your limits, everything we did for derivatives included by the definition, everything we did for implicit differentiation, average rate of change, things of that sort. Those are all be on the test. So when I post the review and the instructions, I'm going to tell you, okay, these are the topics that you need to know for the test. You're going to study those topics, pretend that the mock test is a real test that you're studying for. So don't look at it ahead of time. I want you to be surprised when you look at it, so you can feel what the test might feel like when on Friday you look at it for the first time. So yeah. So I'll tell you what you need to study, and then I'll post a mock test. Do the mock test. It will kind of tell you where you are, what you need to work on, and yeah, you can follow up with me throughout the week, next week. But as long as you're ready by Friday, everything will be fine. So, yeah, that's that. So. think now we're gonna move on. So the last example we did was, we actually looked at van der Waals equation for a specific gas, and we solved for the rate of change of volume with respect to pressure. I just want to just jump into a few more examples here, just to make sure that we kind of have the implicit differentiation thing down. Or better yet, what I would do is, I'm gonna give you guys a couple problems to do, and then so make sure you try them, and if you have issues, now's the time to know what they are. So, so the examples: find y prime first example. So I'll actually give you some time for that. So one problem that will be on the test is there's going to be a problem where I'm going to ask you to just do a bunch of derivatives. So it's going to be like 5 derivative problems. There's going to be a problem A, B, C, D, E. Find y prime in all of these situations. 4 out of 5 of those situations is going to be like derivatives that we've been practicing like the past 3 or 4 classes. One of those problems is going to be an implicit differentiation problem. So you're going to see an expression like this or something else, and where the x's and y's are mixed together, and you need to find a y prime. So you need to make sure you know how to do a problem like this, because I'm definitely going to ask you about it. So that being said, for each of those problems, I would budget 2 to 3 minutes. So I'm going to give you 8 minutes to get through these problems, just to ease our way into it. So actually try those. finish the first one? We're halfway done. Anyone get to the second? Finish the second. Finish both. If you're getting stuck somewhere, at least try to articulate why you're getting stuck. Like, what about the problem's confusing you? Try to actually put that in words. So if you're talking to me or a tutor, you know how to explain where you're lost as opposed to, I don't know anything. Like, that doesn't help anything. Try to specifically say what's confusing. Let's do this. Problem 1, what do we do? Problem A. Yeah.
So I started off by doing the power rule for 4x squared, so I got 8x. And then plus, I did like the product rule for this one. So then you get 2x y prime plus 2y. And then this, again, the multiple or the product rule for that term. So
Yeah.
you get minus 6x y squared minus 3x squared 2y times y prime equals, and then I got negative over x.
Alright, so that's the first step. Go through and just differentiate everybody. Don't forget your derivative rules. So power rule applies here. Here you had two functions, the 2x and the y. You have to do the product rule. Here you had two functions, minus 3x squared and the y squared. You have to do the product rule. So you did that. Yeah, now what?
And then I got all the terms with y prime over on the left and move everything else to the right.
Alright, so we want to isolate the y prime, so you're going to move everyone without him somewhere else. So let's move everyone without the y prime to the right. So we're going to have that minus 1 over x. And then what? Where did you?
Oh, sorry. I got 2xy prime minus minus 3x squared 2y prime.
Just write that as 6x squared y, right?
Yeah.
And then,
And then that will equal 6xy squared minus 8x.
bring this over here, 6xy squared
Yeah,
minus 8x
and then minus 2y.
minus 2y. That's everybody. And in fact, over here, your y prime is a common term. You can factor that out. So now your y prime looks like what?
Negative 1 over x.
That whole mess
Yeah.
over there.
All that over 2x minus 6x squared y.
That's the derivative. Now, if this were the textbook, they'd probably do something like multiply by an x over x to get rid of that 1 over x, but this is fine. Like you get here, you're fine. What about, any questions on this one? Did you do it? Did you go?
I did the u prime times e to the u rule, so
So we know the derivative of e to the u is u prime e to the u, okay?
I did, the derivative of the exponent, which is 1 plus 2y, y prime, times, e to the x plus y squared.
Right, so that's like this here is your u in that formula. Okay, so yeah, that's the derivative of the first part. Second part,
And then I added, 1 over x plus y because the ln is like the outside function. So it's 1 over x plus y, and then, times 1 plus 1 because the derivative of the inside is 1 plus 1.
no, that's not derivative inside.
Okay.
What is off here?
Do you have to multiply by y prime?
Right, whenever you're differentiating the y, you have to multiply by y prime, so derivative inside is
1 plus y prime.
1 plus y prime.
Okay.
And that's just using the u prime over u. The derivative of ln of u is u prime over u. And this here is like your u. So remember, derivative of x is just 1. Derivative of y, think of it as an inside function, it's y prime. Derivative of 3?
0, sorry.
0. So now we have the task of isolating the y prime. And so this is kind of where the algebra is going to come in, right? So it's not like I'm directly asking you an algebra problem, but if you need to solve for that y prime, you need to know how to use algebra to isolate that. Right? So I have a y prime here, I have a y prime here. How do I isolate them? Yeah, you can.
I was kind of confused on this one because I tried, like just factoring out the y prime, can't really like do that.
Yeah, you can't do that because of this 1 and this 1 here.
Yeah.
So-
So could you move that second term, like the 1 plus y prime over x plus y to the other side, and then ln both sides?
Right, but if I did that and threw an ln out here, now this y prime gets trapped inside an ln. How would I isolate him after that? Yeah, so you don't want to trap it inside an ln. Yeah, Laura?
Could you divide by x plus y on both sides?
Why divide?
Because then everything would be in the numerator and then you would be able to
Oh,
factor
you mean
out.
multiply, multiply both sides by x plus y. You mean multiply by the
Sure.
x plus y?
I originally thought multiply, but then I was thinking dividing.
Well, no, you'd have to multiply by x plus y in order to cancel this.
Okay,
Right?
okay.
So you can multiply both sides by x plus y. So what would we have here? So we would have x plus y, e to the x plus y squared, 1 plus 2y, y prime. Here I have plus 1 plus y prime equals 0. So now we don't have any fractions. So in that situation, how do we isolate the y prime? Yeah,
Can you just like combine terms and factor out the y prime?
how would we do that? Because y prime is not a common term at this point. Yeah,
And subtract one
okay,
and put that on the other side and then divide by x plus y, x plus y squared. So it'd be 1 over that.
okay,
And then subtract 1 again from that, like middle term, 1 plus 2y to the y prime. And then you can factor out y prime with that. And then you'll have y prime times 2y
yeah.
plus 1, right?
That makes sense, that could work.
And then
Um,
you have to divide that too, you get like a crazy.
Yeah, I probably, so that would work, your strategy. Personally, I prefer to actually just expand the brackets, right? Normally when you want to solve for something and it's inside parentheses, you just expand. Right, like if you were in another situation, you had like 2 times x plus 1 plus x equals 3 or something like that. How would you solve for x? Like your first step would be just to multiply this out. Right, and then combine the like terms, right? So I wouldn't really think of in divisions and all that. Like I'm just thinking, how would I deal with this in the simple case, right? Sometimes when things look scary, you forget how to think, but you just want to think, well, if this was just some random number, what would I have done? Well, I would multiply out, that's what I would do. And so that's how I would do, just multiply this out. So it's this whole thing times 1. And then this whole thing times that. And now, my y prime is a common factor in these two parts. So if I leave it, I can factor it out. I have 2y x plus y e to the x plus y squared plus 1. And then these two guys, I move them to the other side. So it's minus 1, gets rid of that. Minus x plus y e to the x plus y squared, gets rid of that. And then now I just find the y prime. Just now divide by the common factor. So my y prime I did that one. So this one you have to remember how to differentiate e to the u and ln of u. Like I said, there'll be a problem where one part will be to do a problem like one of these. Now we're going to use implicit differentiation to derive another formula that will be convenient, as well as to help us with another technique. So let's segue into that. We know how to compute, if I ask you what is the derivative of x to the n, we know the answer to that. One thing I want you to recognize here is that where x is the independent variable and n is a constant. Right? So that's like so example, the derivative of x to the 7th, right? You see something like that, you'll know how to actually deal with it. We actually have a formula for that, 7x to the 6th, right? We know how to do that. Now I want to talk about two other kinds of expressions that at first glance might look like that one, but they're actually very different. What about derivatives like those guys? Right? Now, at first glance, they both look like something raised to a power, but it turns out that the power rule actually does not apply. The power rule applies when the base is a variable and the power is a constant. Notice in this situation here, your a is a constant. Right? When your base is a constant, the power is a variable, these two guys are actually very different. Remember, that guy is a polynomial, this guy would be an exponential. This guy grows a lot faster, right? They behave very different. Their slopes are going to behave very differently. This one, the base is a variable and the power is a variable, right? So if you encounter guys like these, do not think that, oh, just bring the power down and subtract 1 from the power. It does not apply to these situations. All the rules I gave you, they apply to the specific situations that the rules talk about. What if I made a variation on this? Switch what's the constant and the function, right? So instead of x squared or x to the 7th, what about 7 to the x, right? Compared to x to the 7th. Or what about x to the x, right? Or x to the x squared or something like that, right? How would I deal with situations like that? How would I find derivatives in this situation? The power rule does not apply. Just because you have something to a power rule doesn't mean the power applies. The power rule applies when the base is a variable and the power is a constant. If you do not have that situation, you cannot use the power rule. So how do you deal with these situations? Here's a trick. And it is something that we've used before actually, but let's remind you. So let's say I wanted to figure out how would I differentiate something like this. What I can do is I can set y equals this function and know that I want to find y prime. Okay. So the fact that the power is a variable and I don't have a formula that deals with that, that makes having the power a complicated thing. So my first inkling would be, can I get rid of the power somehow? And given that my a is a positive number, yeah, I can get rid of it by using logarithms. Logs gets rid of exponentials. So you can actually log both sides. Then what I can do is I can now move that power down by the laws of logarithms. So that's x ln a. And then, now I can differentiate implicitly. Right? The y isn't isolated on one side. So I just go through and differentiate normally, but whenever I differentiate a y term, multiply by y prime. So the left side gives me y prime over y. The right side, ln of a is just a constant, so this is just x times a constant. How do you differentiate x times a constant? It's just a constant. So that side is just ln of a. And so now I can solve for y prime. And that's just y times ln of a. Yeah.
Can you just explain why x ln a equals ln a?
We derived a long time ago that the derivative of a constant times x is just a constant. Right? So this is just a constant here. Right, if a is a constant, the log of it is just a constant.
Thank you.
So once it's a constant times x, the derivative is just a constant. But what was y? Well, y was a to the x. So that's my y prime. Turns out that this is a rule that we know now. The derivative of something that looks like a to the x is a to the x ln a, where a greater than 0 is a constant. So if your base is a constant and the power is a variable, you end up with a log showing up in there. One thing you can appreciate here is if I set my a equals to e, the number e, I would get the derivative of e to the x equals e to the x ln of e, but ln of e is 1, so it includes the e to the x formula. So for example, and so this is like a new formula. For example, if I wanted to, what is the derivative of 7 to the x? Well, it's going to be 7 to the x ln of 7. That's going to be the answer. So if you see something like that, the power rule does not apply. This rule applies, right? The base is a constant, the power is a variable, that's the rule. Of course, with chain rule, we can generalize. So if that would say, I'm taking the derivative with respect to x of a to the u, right? So it's not just an x up there, it's some function. Then that's just going to be, the chain rule says, differentiate the outer function and multiply by the derivative of the inner function. So that's the chain rule version of the function, of the rule. So, for example, let's say I wanted to find the derivative of 3 to the x cubed plus 1. Well, that's like now the x cubed plus 1 is like my u. So the derivative is going to be u prime 3x squared times 3 to the x cubed plus 1, your a to the u, times ln of 3. And that would be your answer. So that's how you would differentiate something like that. Now, this process, what I just did to figure out that rule, where I just used a logarithm to simplify things so that I could find what the derivative is, it's actually a technique. And it has a name. The above technique is called log differentiation or logarithmic differentiation. Right? This is when you put a logarithm into the problem to make it easier to deal with. And of course you have to end up fixing it so that you actually didn't change the value of anything. It's called logarithmic differentiation. So if you're given y equals f of x, we may find y prime by 1, log both sides, and simplify the right side. So this is usually when the function you're looking at is complicated in some way that a logarithm can be helpful, right? We know that logarithms turns powers into products, it turns products into sums, turns sums in terms divisions into subtractions, right? Logarithms can simplify a lot of things. 2, so you're gonna log both sides and you're gonna simplify the right side, which is what I did here. I log both sides, simplify the right side. 2, you're gonna differentiate implicitly. With respect to, say, x. And 3, just solve for y prime. That process is called log differentiation. Let's do another example. If I wanted to find the derivative of x raised to the x power, first thing I'm going to do is appreciate the power rule does not apply, because for the power rule, the power needs to be a constant, and it's not. The second thing you should appreciate is that this rule that I just gave you also does not apply, because for that rule to apply, the base needs to be a constant, and the base here is not a constant. So we don't have a rule for this yet. So what we can do is log differentiation. I can set y equals x to the x. I can log both sides. This will allow me to bring down the x power. And at this point, I would differentiate both sides. This is y prime over y. What's the derivative of x ln x? Huh?
1 over x.
1 over x. That's the derivative of ln x. What is x ln x?
1 plus ln.
How do you get that?
So you would have to do the product.
Right, you need the
So
product.
you do
Two
x,
functions.
x times 1 over x plus ln x times 1.
Differentiate the ln, leave the x, then differentiate the x, leave the ln. So you'd end up with 1 plus ln of x. And so now, you can solve for your y prime. It's just going to be y times 1 plus ln x. But what is your y? Well, it was x to the x. And you figured that out with logarithm. That's not a rule, you don't have to know that by heart. But you should know that something like that, you'd use a log differentiation to actually figure it out. But yeah, that's gonna be that. Let's do some more examples. Now, in practice, I'm not necessarily going to tell you to use log differentiation. It is going to be something that you need to recognize that you can use log differentiation. Use log differentiation to find the derivatives. Say I have 3 to the y plus say find the derivative e to the x squared plus x to the x squared. Find the derivative. Now in part C specifically, technically you can find a derivative without using log differentiation, but it's not going to be fun, right? You're going to need the chain rule with a quotient rule, and inside the quotient rule you're going to need a product rule and a chain rule again. Like it wouldn't be nice to actually attack it directly. However, if you can get a log in there, it's actually going to be a lot easier to deal with. Compared to that example that I gave you guys when we were going through those like 19 or 20 problems. We're at the ln of this complicated thing. We didn't need the u prime over u. We just used the ln to simplify it, and then it was actually super easy to do. So try those. We will take care of that next time, but that's it. This covers everything that we'll need for the test. So on Tuesday and Wednesday, I'll just continue teaching. Whatever I teach after that, though, on Tuesday and Wednesday, I'll probably maybe put on the bonus for the test or something like that. So technically, for test 1, you need to know up to this. Yeah.
So this is it.
Yes. So if I ask you to differentiate something like this on test 1, I expect you to know how to actually deal with it. See you guys on Tuesday.